SwayamPrabha. Digital India. Educated India.
Welcome back to another lecture on control systems. We shall continue to discuss this property of observability, which we started taking a closer look at from the previous class. So first of all, let us quickly cast our attention back to this particular realization. So we had this y triple dot. Let me just, at the cost of boring you a bit, still write this again, a2y double dot minus a1 y dot minus a0 y plus b1 or rather b2 u double dot plus b1 u plus b1 u dot plus b0 u. Yeah, and then we integrate both sides thrice, and then the realization that we get is as follows. Let me try to make this clear and concise. Okay, so you'll have a summer at the end of each of these. Okay, you'll have another integrator, you'll have another summer here, you'll have another integrator likewise here. Yeah, okay, so let's try and see, look at all of this. So this is our y. So we know that this y, the rightmost variable we name as the output, which is the y, and at the input channel we have u, alright. And then we know that what is after all this y triple dot. So if we integrate this thrice, we will get that y is equal to minus a2 integration of y. Okay, I am just omitting the dt, you understand what it means, minus, this is just symbolic, minus a1 twice the integration of y minus a0 thrice the integration of y plus b2 integration u plus b1 twice the integration of u plus b0 thrice the integration of u, right. So we know that we have to send this b0 times u thrice through this integration in order to get y, then we have to send b1 times this u twice through the integration. Yeah, so we just push this through b1 and then we bypass the first integrator and we pass it through the remaining two integrators, and then we know that we have to pass this fellow b2 times once through the integral action. So we bypass the first two integral actions and we just pass it through the third integral action, right. So that takes care of these three terms. Now what we are required to do is to account for these other remaining terms. So for that, you see, you have to pass y through an integration once upon scaling it with minus a2. Yeah, so let me scale it with minus a2 and pass it through once. So this is also going to be a reprisal of sorts. We are going to again look at the state space realization of this form. Now we are going to give it the name. This is the observer canonical form, and you will see that this is always identically going to be observable. If you realize a transfer function or an ODE in this form, in the observer canonical form, it is always going to be observable, right. Okay. So what is this going to pass through? Twice we need minus a1, right, and finally when you have to pass it thrice through the integral action, it better go through a0. So minus a0, I knew it, I was missing a trick, so I missed this summer here, sorry about that. Yeah, so here's this summer, yeah. All right. So this is the kind of realization of a system. Of course, this is not limited to just third degree differential equation, you can make it nth degree. The general structure is always going to be like this, okay. This is going to be the general structure of the realization of the differential equation of degree n. You can imagine there will be a bank of n integrators now. So now you call this variable as x1, so this is your x1 dot, this you call as x2, this you call as x2 dot clearly, this you call as x3 and this you call as x3 dot, alright. So now what can we say about this? Well, let's carefully write the state space equations. So you see the x1 dot is going to be equal to minus a2 x1 plus a2 x2 minus a2 x1 plus x2. What is x2 dot? Well, x2 dot is going to be minus a1 x1 minus a1 x1, okay, there was a plus b2u as well which I missed, sorry about that. So x2 dot is going to be minus a1 times x1 plus x3 plus b1 u, and finally x3 dot is going to be minus a naught x1 plus b naught u, yeah, yes, I guess that is what the structure is going to be, right, yeah, minus a naught x1 plus b naught u, right. What about the C matrix? The C matrix is going to be just 1 0 0 times x1 x2 x3. So the Cx is going to be like this, yeah. So this is my C matrix. What is the A matrix? So if I write this down carefully now, this is minus a2 minus a1 minus a0, and you see this is 1 0 and this is I guess 0 1, yeah, and this is 0 0, yeah. So that is the A matrix. So now we are interested in finding out what C Ca Ca squared looks like. So of course C is basically nothing but 1 0 0. Look at Ca. What does Ca look like? So Ca is going to just filter out the first row of this A matrix, that is minus a2 1 0, that is going to be minus a2 1 0, and then look at Ca squared. So that is going to be the Ca times the Ca squared, so that is going to be nothing but Ca times this A, right. So if I now take this minus a2 1 0 and pre-multiply A with it, then that is basically going to be minus a2 squared, so it is going to be, right, it is going to be, sorry, a2 squared minus, I think there will be something, no, so hang on, minus a2 1, so minus a2 times minus a2, that is a2 squared, and this is, so minus a1. So a2 squared minus a1 is the first term. What about the second term? The second term is minus a2 0 0, yeah, so it is going to be just minus a2, minus a2. What about the final term? Final term is just going to be minus a2 times 0 plus 1 times 1 plus 0, so that is 1, So that is 1. So now if I write this CA squared, which is only as far as I need to go for the observability matrix, yeah, because of course this is a third degree differential equation, so I need to go only till n minus 1, which is 2. So then look at this matrix, I get 1 0 0 minus A2 1 0 and A2 squared minus A1 minus A2 1, and clearly the determinant of this observability matrix is always going to be unity, independent of these A1, A2, A3 parameters, and that is exactly the reason why we said, because the determinant, you see, if you expand it by the first row, 1 times 1 into 1 minus 0, and that is it. So it is always going to be 1 independent of the parameters. So that means it is a function of this realization, right. So of course it is trivially true, now you can take this as an exercise in mathematical induction, yeah, that any matrix A that is of this form of size n cross n, and any matrix C that is of this form of size 1 cross n, where only the first entry is 1 and the rest are all zeros, if you operate this and obtain the observability matrix like so, you will always get a lower triangular matrix with 1 sitting on the diagonals, right, which basically tells you that the determinant of such a square matrix is always going to be 1. So as I claimed in the previous day, I have now shown you, at least for the 3 by 3 case, and you can take this as an exercise to prove it for the general case, yeah, it is really not a big deal. I could have actually taken it just n by n here also, and a bit of mental gymnastics would have led you to conclude that indeed it is always going to be like this. So that is why this property of observability, as will be the property of controllability that we shall see next, yeah, these are all features of the way you are realizing the system. Yeah, so we are going to now see next that if you take this similarity transformation, alright, then it turns out that if you start from an observable or an observable system and you take similarity transformations, then the resultant system will also be observable, yeah, and that is something very important, yeah. So we shall see that now, okay. So suppose A, B, C, D is observable, alright, suppose A, B, C, D is observable, yeah, let A bar, B bar, C bar, D bar be such that, let A bar, B bar, C bar, D bar be such that A bar is equal to T inverse AT, B bar is equal to T inverse B, C bar is equal to CT, yeah, and D is equal to D bar. So that basically means that, you know, this is a similarity transformation that you are performing on this original system to get this second system, which is this represented with this bar matrices, right. Now consider the observability matrix of the original system, sorry, observability with AC, right. So that is going to be what? This is going to be CA square dot 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 till CA to the power n minus 1, right. And next consider the observability for this similarly transformed system, rather if I call it AC, yeah, let us call it A bar C bar instead of C bar A bar, really not a big deal, but yeah, let us be consistent, yeah. So now we have this C bar A bar, likewise till C bar A bar to the power n minus 1, right. So we understand what this is. Now if you want to write this in terms of the original matrix, then we get C bar T inverse, sorry, CT, which is basically my C bar, remember that is what C bar is, right, and then this is CT times what I next write is T inverse AT, which is basically nothing but this, right. So now you see in between this T and T inverse will pulverize each other. So likewise in the last term also it is what? It is nothing but Ct, then T inverse At, T inverse At, likewise still you keep repeating n minus 1 times, and finally you have T inverse At. So you see all these T's in between, they all cancel out because they pulverize each other. So what you get basically then is Ct, Cat, Ca squared T till you get Ca to the power n minus 1 T. If that is so, then remember that this T is basically an n cross n matrix. So I can pull out this T from the right hand side, and what I get is, it is basically the observability in terms of the original system times T. So remember this is an n cross n matrix, this is an n cross n matrix, right. Now what do we get? So therefore we have this observability in terms of A bar C bar given by the observability in terms of AC times T. What do we know about T? T is n cross n and non-singular because it is a similarity transformation. Therefore the matrix using which we got this similarity transformation must be non-singular, so it must be invertible. Yeah. Now suppose, so now we have seen that ABCD is observable. Yeah. So now consider ABCD is observable, so therefore consider T inverse OAC inverse. Yeah. Okay. This exists since T is invertible and OAC is also non-singular. Non-singular square matrix means its inverse exists, yeah, because its determinant is non-zero. If its determinant is non-zero, then of course you can take the adjugate of that matrix divided by the determinant if it is non-zero, and that is going to be the inverse. So therefore this exists. Therefore O times O in terms of the bar representation, the similarity transformation, times T inverse O AC inverse is going to be what? Is going to be nothing. Now I am going to replace this from here. What is this going to be? This is going to be O times AC times T times this T inverse, which I am now replacing here, T inverse O AC. Yeah. So this T and T will again pulverize each other. Yeah, and this is the inverse, right? So let me put the inverse in the proper place. Yeah. Let me put the inverse where it belongs, in the proper place. Yeah. So this is it. So therefore this two will pulverize each other and you will get an identity in the middle, and then OAC and OAC inverse, that will also give you identity. So this is actually going to be identity. So therefore what I am saying is that this matrix, yeah, this matrix, and whether you take it the left inverse or the right inverse, so if you hit it with this fellow on the right, on the left, if you had hit this fellow on the left also, you would have still gotten the same thing, right? So therefore this is identity. So therefore this blue fellow is the inverse of O A bar C bar. What does that mean? That means that this observability matrix of the transform system is also invertible, which means that the transform system is also observable, right? So that is what I am claiming. If you take an observable realization, an observable state space realization, and if you want to go to another realization through a similarity transformation, right, then that new realization will also be observable, even if it may not look nice. So that's a beautiful thing. Why? Because remember, we just discussed that this observer canonical form is always going to be fully observable, right. So now you take any other form from this observable canonical form through a similarity transformation, you go to any other form. Now in that particular form, that observability matrix may not look very nice, but the fact that you have come to this new form, this new realization starting from the observer canonical form, tells you that this new realization must also therefore be observable, okay. So that is a very important property, right. So what about the question about the other way around? In other words, what we have just seen is that if you have an observable realization of a transfer function, right, and then from that state space realization which is observable, if you take a similarity transformation, you land up with another realization which is bound to be observable. Why? Because the observability matrix in terms of the transformed system matrices is also going to be of full rank or invertible, right, that is what we have seen. So the other way around, the question can be posed as follows, that suppose someone sitting here in maybe locations 1 and 2, so someone sitting in location 1 designs an observable realization for a transfer function, for a given transfer function, and someone sitting in location 2 designs another observable realization, yeah, for the same transfer function, right. So is it guaranteed that there is going to be a similarity transformation between this realization 1 and the realization 2? In other words, we are going back to that question that suppose you have this transfer function or ODE, yeah, which is given to one person here who realizes it. So this is SSR1, this is observable, yeah, and there is this other person who also realizes this, but it is a state space realization 2, and this is also observable. Now the question is whether there exists some T inverse or some T, rather some invertible non-singular matrix T, which takes me from this one realization to the other. Is it guaranteed to exist? That is the question which now interests us, right? Because if that answer is yes, then we will have a partial answer at least to this question that we posed right at the beginning of our discussions on state space systems. Remember, we had this ODE or state space this transfer function to start off with, yeah, and we said that at the first level you generates different realizations, right. So we saw at least two of them. One was this phase variable form, the other was of course what we now know as to be this observer canonical form, right. Yeah, so this is SSR1, SSR2, so on, this is SSRn, let's say. So you did keep generating many more of these. Now under what condition can we be assured that between these state space realizations there always exists a similarity transformation? We have seen a partial answer, a smaller partial answer before, in that if you take any of these fellows to start with and then you take a similarity transformation and you generate many more of these, yeah, then between any two such fellows belonging to the same bag here, yeah, they can all be related through a similarity transformation. Similarly, you take this and and obviously you take this and take it to another realization through a similarity transformation, and yet another realization through a similarity transformation, then these two are also related by a similarity transformation. So everything in one of those bins or bags is related by a similarity transformation, but we do not really know what sort of a property characterizes, what is common to them. But now if the answer to this question, so this is our question here, if the answer to this question is yes, if it is yes, right, if there is guaranteed to exist such a similarity transformation between any two observable realizations of a given transfer function or ODE, then we know at least some system theoretic property to look for in order to be able to connect different state space realizations through a similarity transformation. Here of course it is explicit, no, you go from here to here through a similarity transformation, here to here through a similarity transformation, then you know what is the similarity transformation between these two. We have already seen that in an earlier lecture, right? But that is really not a system theoretic property, yeah? It is just some choice of a matrix that we have made, some non-singular matrix. But now we have seen that since this property of observability is invariant to similarity transformation, it just begs the question that is it true that if you and I independently get two observable realizations of the same transfer function, right, then can they be always related using a similarity transformation? A small thing needs to be clarified here. When I say the same transfer function, right, it essentially means that a given transfer function can be written in this fashion, yeah, and it can also be written in this fashion, ns upon ds times some qs by qs, right. So what I mean by state space realization of the same transfer function, I am not referring to these different realizations. So for example, if I were to realize this transfer function and you were to realize this transfer function, for starters, you see the degree of the denominator polynomial in my case will be smaller than the degree of denominator polynomial in your case. QS is an additional polynomial, a common factor, right. So obviously when I am saying it is the same transfer function or same ODE, I am not referring to these, right. So you might in your bid to prove me wrong, yeah, you might choose these two different representations and you might say, oh look, at the heart they are the same transfer function, after all that q is common, it will cancel out. But well, then you better cancel it out, because without cancelling it out, if you want to look for a similarity transformation, it is meaningless, because I will get an A matrix of a size which is different from yours, right. So that is a question again which will be related to minimality, which we will like maybe discuss in a few lectures from now. But I just want to make sure that you understand, when we are saying it's the same transfer function, we mean exactly the same transfer function, right. So we are not cancelling out some factors that you are not cancelling out some factors which I am not, and I am not cancelling out some factors which you are not, right. So we are basically dealing with the same poles and same zeros, right, and the same constant gain. Only then do we call them the same transfer function, okay. So in order to answer this question, I will introduce a bit more of theory, which might seem like a digression to start with, but rest assured we will again head back to this question, and by the end of this lecture we will have answered this question hopefully rather convincingly, right. And it turns out, spoiler alert, that the answer is indeed a yes, we can, right. So before we get into that answer, let's build the groundwork for that. So let's just try and understand a few system theoretic results here. So what I am saying is, if A, B, or rather A1, B1, C1, D1 and A2, B2, C2, D2 are such that C Si minus A C1 Si minus A1 inverse B1 plus D1 is equal to C2 Si minus A2 inverse B2 plus D2, yeah, then C1 e to the power A1t times B1 is equal to C2 e to the power A2t times B2, and D1 is equal to D2, okay. So this is the first important stepping stone. Now notice something very important here, okay. The important thing that I want you to note here is, unlike in the previous case, so this result is more generic, this result is more general, because here it could be, and here is why it is critical, because we will call upon this result and its related results quite often subsequently. So it is important to understand that here, unlike in the previous case where I told you that this GS must be represented in the same form, there cannot be like you are considering the numerator as NSQS and I am considering it as NS, and you are considering the denominator as DSQS and I am considering it as DS. Unlike that, here, yeah, it turns out that A1 could be of the size N1 cross N1 and A2 could be of the size N2 cross N2, yeah, where N1 need not equal N2, okay. So while I am proving this result, while I am trying to get to this result, it is not important it is not at all important that n1 and n2 have to be the exact same. In other words, there might be some pole 0 cancellation in one of the realizations and there may not be those pole 0 cancellations in the other realization, but nonetheless, you see, if those transfer functions agree, right. So when you get the transfer function from the state space realization, we will both get the same transfer function. So here is the thing, okay. So we start from a transfer function and we get to a state space realization, yeah, and let us say you start from another transfer function which is basically nothing but a scaled version. I mean, I would not say scaled version, it is basically just adjusting the numerator and denominator by this QS, right. So what I am saying is at the heart those transfer functions are the same, but only that one of the transfer functions has the same common factor multiplied both at the numerator and the denominator, right. And then obviously we will end up with different state space realizations. For one, their sizes will itself be different, as I have just said, right. But the crucial important detail is that once you derive the state space realization back again, yeah, so let us say this is my state space realization 1 and this is my state space realization 2. So this is transfer function such that this is transfer function 2 and this is transfer function 1, and transfer function 2 is equal to transfer function 1 times some QS upon QS, okay. So it is basically the same transfer function as TF1 except that there is some common factor in the numerator and denominator. So obviously we will get two different state space realizations and they are not even compatible size wise. So the question of similarity transformation does not arise. But the point is, now if you take C Si minus A1 or C1 Si minus A1 inverse B1 plus D1, and if this other fellow takes C Si minus A2 inverse B2 plus D2, yeah, they will both end up with the same transfer function, yeah, which will be indeed what is called the minimal transfer function, okay, minimal one. So that means after all common poles and zeros are cancelled out, okay. So this might seem a little confusing to start with, so let me go back 2 slides and explain this clearly. So far whatever we have been talking about, when we say that we start from the same transfer function and ODE, we mean explicitly that we are talking about transfer functions which are absolutely identical. So there is no common factor in one of the transfer functions, and if that common factor is present in one of the transfer functions, then it must be present in the other guy's transfer function as well, right. So when we say it is the same transfer function, we do not mean that we allow these transfer functions to take these two different forms, yeah, they must appear in the same form. So I must be realizing the transfer function in exactly the same form as you are. Let me give an example. So suppose the transfer function is s plus 1 into s plus 2 upon s plus 2 into s plus 3. So if this is the form of the transfer function that I am realizing and you are realizing the transfer function s plus 1 upon s plus 3. Now you might argue that after all this GS and this GS are the same. So this is G1 and this is G2, so you might say that G1 is equal to G2, but for the purpose of realization they are not the same. And when we are talking about realizing a transfer function from here, we are disallowing this sort of equality, okay. We are saying that if G1 is equal to G2, then this is not the sort of equality that we want. We want equality in every sense. So the degrees of the denominator polynomial, the poles, the degree of the numerator, the zeros, they must all be identical, yeah. So I cannot be realizing G1s and you should be realizing G2s and then we compare our respective realizations and say whether there exists a similarity transformation. It is a meaningless question, right. That is it. So that is what we have been talking about so far, in case I have not clarified that. So that is what we have been talking about so far. But now we end up with this result here where we remove that restriction. This is generic irrespective of whether, so this result is independent of the problem we are investigating. We are investigating this problem of whether there exists a similarity transformation between two state space realizations originating from the same transfer function, same in this sense, yeah, not in the sense like these two are same. So same means They are both ns by ds, where ns and ds both tally, right. But this result does not care. In this result we are saying that you could have common factors, so long as the effective transfer function after cancelling out the pole and 0 is the same for both the systems, right. N1 and N2 need not be equal, even then this result is going to be true. This result and this result is going to be true. So in other words, what this result is saying is that if you look at this GS, yeah, as a map from this US to YS, yeah, then these two maps are identical on this side, yeah. So if you are talking about this realization, this ABCD is a map from the input to the output, this A to B to C to D to is also a map from input to the output. So insofar as their input to output map is concerned, we are not talking about the initial condition, because obviously if the sizes of the A matrix are different, then the sizes of the states are different, the state vector, and therefore obviously there is no question of comparing initial condition or zero input response. But we are talking about the zero state response, the forced response, okay. And there we say that if you look at it as a map from the input space, the space of input signals to the space of output signals, then they are identical, yeah. So the claim is that if that is so, then these two conditions must hold, yeah. So we do not care about the state space realization anymore, we are just looking at it as a map from U to R, U to Y, right. So in that context now we are trying to derive this result, and while deriving that result, now I have shown you that, well, if you have even if you had this two different sizes of the A matrix, yeah, they will lead to two different state space realizations naturally. Even the sizes of these two state space realizations need not be compatible, SSR1 and SSR2. So this can be of degree n1, n2, and this can be of degree n1, yeah. So this is an n2 cross n2 realization for A, yeah, and this could be like A1 belongs to n1 cross n1, yeah. But irrespective of that, if you now take this map, you will see that you end up with the same transfer function. So you don't, so this does not take you back to this transfer function, and this does not take you necessarily back to this transfer function. When I said that, yeah, earlier, now you might hold me to it, and you say that earlier you said that, well, if you go from the transfer function to the state space and then state space to the transfer function, you showed that the root was the same, but we were not really equipped with all the sophistication at that point to talk about it. But strictly speaking, we do not necessarily go back to the exact same form of the transfer function, yeah. You start with the transfer function, take its state space realization, and then apply the CSI minus A inverse B plus D. You go back to the, ideally speaking or technically speaking, the same transfer function, but not exactly in the same form. You go back to its minimal form, okay. So this TF3 effectively is equal to both TF1 and TF2, yeah, but technically speaking this TF3 is basically the irreducible form, the minimal form of the transfer function, and TF1 and TF2 could have some common pole zero cancellations occurring there, right. So that is why in that sense it is a little different. So I hope that point is clear. So that was a bit of a digression, again, digression within digression. Already this is a digression, right, an apparent digression, if you permit me. So right, so now we want to prove this result. So how do we go about this? We will not really get into a rigorous proof of this, but just please do note that if you want to write this state space representation, so what is Y? It is a map from U to Y is what we are interested in, right. So we are doing it in the time domain. So in the time domain, this response is going to be nothing but this 0 to t e to the power a t minus tau b u tau d tau plus d ut, yeah. So let us say we take it in terms of the first system, yeah, and then this is also in turn equal to, because if they are representing the same map, then these two better be equal, yeah. This is the map basically, you feed in and you pass it through this operation and you get Y. So if you are passing it through both the maps, you should end up getting the same output at all instants of time, right. If you get the same input, you should get the same output, right. So then note that Y0 is equal to D1 U0 is equal to D2 U0 for all ut, Yeah, what does this imply? So if u0 is not 0 for some input, then it just implies that d1 is equal to d2. So this is a no brainer clearly, yeah, because note that both these maps are identical. So at t is equal to 0, yeah, for any input that you give, yeah, for at t is equal to 0, these two must agree because of equality between these two. So I am just plugging in t is equal to 0 and I get d1 is equal to d2. So therefore now this, so this is going to be C1, right, this is going to be C1, that is the state space equation, right, you have to pre-multiply by C. This is true since both maps are identical. So what we are saying is that both these maps in terms of A1 B1 C1 D1 and A2 B2 C2 D2, they are representing the same map from U to Y, so they must both be equal, and if they are both equal, then by just applying t is equal to 0, I get the condition that d1 is equal to d2, which is one part of the claim. This part of the claim is now taken care of. Now I have to prove this part of the claim. So now once I have shown that this part is equal, then it just stands to reason that this part is equal for all u, ut, yeah, and all t, right. So this has to be true then, right, because the other part is equal. So if there is a plus b or x plus y is equal to p plus q and x is equal to p, then y better be equal to q, right. So this was basically what we started off with. So x plus y is equal to p plus q, and we saw that y is equal to q, therefore x must be equal to p. So now we can use this condition, so therefore this must be true. So sorry about that earlier confusion that I created and said to show that. This is not what we have to show. So what we have to show is this, that e to the power, this part is equal. So we have to show that c1 e to the power a t b1 a1t is equal to c2 e to the power a2t b2, alright. We have to show that this must equal, right. So suppose there exists t bar such that c1 e to the power a1 t bar minus c2 times b1 minus c2 e to the power a2 t bar times b2 is not equal to 0. So suppose there exists some t at which this is violated. So we will prove by the contradiction, prove by contradiction, right. So suppose there exists some t bar such that this is not true, then what can we say? Note that, so if I describe this function as ft, yeah, note that f t bar, so f of t at t bar, note that ft is a continuous function, right. So it cannot be that, you know, if it is a continuous function, so here is a subtle little argument. So this is ft, and I am saying that there is this instant t bar at which it is not equal to 0. So if it is not equal to 0, then within some small neighborhood around it also I can always find, because of the continuity argument, so I can find some t bar plus delta and some t bar minus delta around it, yeah, within which it is not 0, right. So therefore ft is not 0 for some t belonging to, let us say, t bar minus delta to t bar plus delta. This is just the continuity argument, right. I can always find some such t bar minus delta and some such delta rather, right. But now note, what does this result in, right. So now choose, remember that this condition needs to be true for all ut, yeah. So suppose now I choose u t is equal to exactly this function, right. So suppose now I choose ut is equal to c1 e to the power a t plus delta by 2, so t bar plus delta by 2 minus t b1 minus c2 e to the power a1 t bar plus delta by 2 minus t times b2, right. Okay. Now notice this implies what? This implies that, hang on, yeah, here it is. So this implies that C1, so let me put the whole integration back together here, C1 e to the power a1 t minus tau, rather let me replace this, t bar plus delta by 2 minus tau, yeah, okay, yeah, C1 times B1 minus C2 e to the power A2 t bar plus delta by 2 minus tau B2 whole times u tau d tau 0 to t bar plus delta by 2, yeah. What must this be equal to? This we know should be equal to 0, right, because we know that for every time instant t and for every input that you apply, so this must be true. So let me just rephrase that. Now we must have this condition, yeah, so this must be equal to 0. Now we must have this equal to 0, why? Because this is after all y of t bar plus delta by 2 evaluated according to the first map minus y of t bar plus delta by 2 mapped according to the second map, yeah, and we know that for all possible inputs that I can apply, both these maps, if I am applying the same input, both these maps must take me to the same output at every instant of time. So at this instant of time t bar plus delta by 2, yeah, it must take me to the same output, right. So therefore the difference between these two must be 0, yeah, the difference of the output obtained through map 1 and the difference of the output obtained through map 2 must be 0. But now notice, if I just plug this in here, what do I get? Now for this particular choice of ut, this means that we must have this integration from 0 to t bar plus delta by 2. Notice this u tau is nothing but exactly this, no, you just replace t by tau here. So then what we get is C1 e to the power a1 t bar minus delta by 2, t bar plus delta by 2 minus tau b1 minus C2 e to the power a2 t bar plus delta by 2 minus tau times the same thing, so it is squared d tau must be equal to 0. But can this be true? See, this is a positive quantity or at least a non-negative quantity. Now this fellow is always greater than or equal to 0, and we know that over some interval at least, yeah, over some interval, so if you are taking this up to this point, this is your t bar plus delta by 2, so over this much interval at least, yeah, this has a non-zero value. We have assumed that, right, that they are not equal at some point. So if they are not equal at some point, then they have a non-zero value over this interval. So this non-zero value, square of that non-zero value, that's getting integrated, so that's basically some non-trivial area. So this is the contradiction, but this is a contradiction. So therefore we conclude that what we started off with assuming, that must be wrong. So therefore C1 e to the power a1 t b1 must be equal to C2 e to the power a2 t b2, yeah, provided that they lead to the same transfer function and of course earlier also we have proved this. So, and d1 is equal to d2. Yeah, so if you have the same transfer function obtainable from two different state space realizations, irrespective of whether those state space realizations agree in size or not, this is a generic result, always true. Remember, the result we are looking for is when the sizes are the same. Yeah, we are only dealing with those transfer functions, but even if they are not same, this result is a very deep system theoretic result, it is always going to be true. And as a corollary to this result, what we next have is, as a typical corollary to this result, what we then have is that C1 a to the power k b1 is equal to C2 a2 to the power k b2 for all a1, b1, c1, d1 and a2, b2, c2, d2 such that C1 Si minus A1 inverse B1 plus D1 is equal to C2 Si minus A2 inverse B2 plus D2. Yeah, so if you start with the same transfer function, yeah, if these two state space realizations, irrespective of their size, they lead to the same transfer function, then you must have that these quantities must be the same. So you might say, well, in multivariable case is it true, like if there are multiple inputs and multiple outputs, remember the size of the state might vary, so A1 and A2 might come from different sizes of matrices, right, but the size of C1, at least the number of rows of C1 must be same as the number of rows of C2, because the number of output channels do not vary. Similarly, the number of columns of B1 must be equal to the number of columns of B2, because the number of input channels do not vary. Whether you are realizing a system using a third order transfer function or a second order transfer function, provided there is a cancellation of pole and 0, that is, yeah, the number of inputs and outputs must be the same. Yeah, so therefore here it's of course C, so it's a no brainer there, right. So therefore this, in our case this is a scalar and this is a scalar, so even if the sizes of A1 and A2 do not match, these are both scalars, so therefore the equality makes sense, okay, and this is always going to make sense even in a multiple input multiple output case, right. So remember, this is a corollary. Why is this true? This is true because quite simply, if you now notice what I have not mentioned, what I have stopped short of mentioning earlier here is that, look, what is this function after all? Yeah, so it's going to be this C Si minus A inverse B plus D, this Laplace inverse. So obviously it will contain this impulse because of this constant term D here. But then again, if you are interested in the Laplace transform or the inverse Laplace transform and you want to find out the time response beyond t is equal to 0, then for all practical purposes you see this is going to give us back that old fellow C e to the power at b, yeah, and D contains only that impulse, so beyond t is equal to 0 it does not have any effect, right. So this is all there is to basically the impulse response of the system. Response and its derivatives and all higher order derivatives must match at t is equal to 0. So we have that this corollary follows from the fact that h dot evaluated at t is equal to 0, or rather h evaluated at t is equal to 0, h dot evaluated at t is equal to 0, h double dot evaluated at t is equal to 0, etc., until all the h, the kth derivative, yeah, evaluated at t is equal to 0. Yeah, this must be the same. So if this is h1 for the first system, the impulse response, this must be the same for h2 evaluated at t is equal to 0 here. This fellow must be the same as h2 dot evaluated at t is equal to 0. This fellow must be the same as h2 double dot evaluated at t is equal to 0, so on and so forth, and this fellow must be the same as the kth derivative of h2 evaluated at t is equal to 0. Yeah, because after all they are going to represent the, provided you give the impulse input, the response will be the same, the impulse response will be the same, and no matter how long you keep taking the derivatives, they must agree in all possible derivatives. So this must be true for all k belonging to the set of positive integers, yeah, for all k belonging to the set of positive integers. So now once you observe that, what is after all the derivative of this fellow? you take the first derivative and you get C1 e to the power, so you can get C1 A1 e to the power A1 T B1, and then you plug in t is equal to 0 and you get C1 A1 B1. Yeah. So I repeat you can keep repeating this process, yeah, and you will get that this result is always going to be true. So therefore we have this interesting result. Okay. So this result is always going to be true as long as this result is going to be true irrespective of the size, that is this result, sorry, where was I? Just a slide back, maybe even another slide back, yeah. As long as this result is true, that C1 e to the power A1 T B1 is equal to C2 e to the power A1 T B2 is true, this result that we have now shown you must also be true. Yeah, so this is true if provided you have the two state space realizations irrespective of the number of states in each of the realizations. One may be a minimal realization, the other may not be a minimal realization, but this result holds true in any case, right, between any two realizations which lead to the same transfer function, this result must be true. So this is an important stepping stone to what we are going to derive hereafter, which is, now we say that, let me get back to now, after a bit of this digression, let me focus our attention back to the original question we started off with, which was that if you start from this transfer function or this ODE, yeah, and you obtain an observable realization, I obtain another observable realization, and both of us will get eventually two realizations which are transformable from one to the other through a similarity transformation. Yeah. So that claim we had yet to substantiate. So we will carry on with this in the next lecture too, but for now let me just make an observation because we have a little bit of time to do that. So consider an observable realization such that obviously the observability matrix, the inverse of this observability matrix exists. So we are talking about CISO, so this observability matrix will be a square matrix, and therefore its system being observable is tantamount to saying that the observability matrix is invertible. Now look at OAC times A times O inverse AC. Okay. So note that O is equal to, so I am dropping this argument here, so O is equal to C CA dot 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 till CA squared, sorry, CA to the power n minus 1, and let O inverse is equal to say some P1 P2 dot 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 till Pn. So these are columns, so these are columns of the matrix, so this is all n tuples. So these are all n tuples. Okay. So what do we know if these are inverses? Then I know that CP1 must give me 1 0 0 0 0, yeah, because if O into this is because since O into O inverse is identity, so C times P1 must give me equal to 0, C times P2 must give me the all 0 vector, similarly C times P3 must give me the all 0 vector, yeah, that's how this, sorry, this is a scalar, no, my bad, I missed this in a hurry. This is going to be a scalar because C is a row vector and P is a column, so it's just a scalar. So C times P1 is going to be 0, C times P1 is going to P1 is going to be 1, because that is a 1 1 entry of the identity matrix, right? Row of this, column of this, right? Notice that this is a row and this is a column. So first row, first column, you get the 1 1 entry, so this is going to be 1. So similarly C times P2, that gives you the 1 2 entry of the identity matrix, which is a 0. So C times P3 is equal to 0. Likewise, C times Pn is equal to 0. Similarly, you look for the second one. So Ca times P1 is going to give you 0, but Ca times P2 must give me 1. Yeah, because this in the second row, the second entry must be 1 and everything else should be 0. So Ca times P3 must be equal to 0 likewise. So likewise, you can imagine that I can keep saying that well, Ca a to the power k times p, what is it, k plus 1, k plus 1 is equal to 1, and c a to the power k p j is equal to 0 otherwise. Yeah, that is the general form, no, that is why you will get the identity after multiplying this. Yeah, so this is the general form we get with the observability matrix and its inverse, where these pk's are p1, p2, p3, these are columns of the inverse of the observability matrix, and the inverse exists because it is an observable realization, right. So now notice that if this is how we plan to go about it, right, then eventually we can generate this, we can generalize this result. Now if I write the observability times a, that is going to be what? That is going to be the Ca squared till Ca to the power n minus 1, and then I have Ca to the power n, and then I have this, if I post multiply by the O inverse, I get this P1, P2 dot 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 till Pn. So what is this going to be? I have already seen the structure. See, this Ca times P1 is going to give me 0, Ca times P2 is going to give me 1. So Ca times P1 is going to give me 0. So this matrix structure, I can say what it looks like. What does it look like? Ca times P1 is going to give me 0, Ca times P2 is going to give me 1, and everything else is going to be 0. So similarly, Ca squared times P1 is going to give me 0, Ca squared times P2 is going to give me 0, but Ca squared times P3 is going to give me 1, like this. So I can go on till this, till the last row, you will see I will have till the penultimate row, the last but one row, and I will have 1 here. So this is going to be like this, these are all going to be 1, 1, 1, 1 like this, no, everything else is going to be 0. What about the last row? It seems like I do not have the recipe for this, right? But now recall the famous Cayley-Hamilton theorem. The Cayley-Hamilton theorem says that if the characteristic polynomial of A is, say, the characteristic polynomial of A is A0 plus A1s plus A2s squared plus dot 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 till plus A n minus 1 s to the power n minus 1 plus s to the power n, then I know that A0 I plus A1a plus A2a squared plus dot 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 till A n minus 1 a to the power n minus 1 plus a to the power n is equal to 0, because every matrix satisfies its characteristic polynomial. This is the Cayley-Hamilton theorem. Yeah. So therefore I have this recipe now. So a to the power n is nothing but minus a to the power n minus a n minus 1 times a to the power n minus 1 minus a n minus 2 a to the power n minus 2 dot 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 till minus a0 I, right. So let me fill that out here in this, let me replace this with c times minus a0 I minus a1 a minus a2 a squared minus dot 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 till minus a n minus 1 to the power n minus 1. Yeah, this is what this is. Now each individual, now this is, note that if I multiply this with P1, it is going to pick out which one. See, C times P1 is going to give me the only non-zero entry. The moment I take Ca times P1, this A1 is just a scalar, no. So if I take Ca times P1, it is going to give me 0, Ca squared times P1 is going to give me 0. So what I get then is, the first entry is going to be just this minus A0. What about the second entry? When I multiply with this P2, you see this second entry times this P2, Ca, this C times P2 is going to give me 0, but the moment I multiply this Ca times P2, I am going to get 1, so it is going to pick out A1. So likewise you see, you will just get this minus A n minus 1. But what are these? Yeah, what are these? These are nothing but the coefficients of the characteristic polynomial, and we have seen that the characteristic polynomial is invariant to similarity transformations and if this is the characteristic polynomial of the A matrix and you start with the same from the same transfer function irrespective of whether there exists a similarity transformation or not in fact, yeah. So if you start from the same transfer function, you are going to end up with matrices, this state space realization and this state space realization. The A matrices, if they are of the same size, they must have the same characteristic polynomial. So now from this we conclude that, and even if two realizations do not have a similarity transformation between them, if they come from same transfer function, the characteristic polynomial must still be same. So if the characteristic polynomial must be the same, it means that, now notice, if I have an observable realization A1 C1, yeah, and an observable realization A2 C2. So this is observable, therefore O inverse of A1 C1 and O inverse of A2 C2 exist, both exist, yeah. Now I perform this O A1 C1 times A times O inverse A1 C1, yeah, and I perform O A2 C2 times A2 times O inverse A2 C2, yeah. What should I get? I should get the same matrix, that is the 0 1 0 0 0 0 0 1 0 0 0, right, then minus A0 minus A1 dot 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 till minus A n minus 1, and here also I must get the same matrix 0 1 dot 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 0 0 0 1 0 0 0 dot 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 till minus A0 minus A1, because this was irrespective of the property. If a matrix, if a system realization is such that it is observable and I take this sort of a similarity transformation, I can do this because it is a square matrix and it is invertible. So this is a legitimate similarity transformation. So for any observable realization, if I take this similarity transformation, I know the exact form of the A matrix that I transform to. So both of these turn out to be the same, right? So if this is the observable realization that I have obtained sitting here in Mumbai, and this is the observable realization that you have obtained sitting there in Delhi for the same transfer function, right? If we both carry out this sort of a similarity transformation with our corresponding observability matrices, we will both end up with the same matrix. What does that tell us? I am putting it to you that we are done, because this just tells us that O inverse, so this let me call this O1, so I want to drop this AC, this argument, so this is O1 A1 O1 inverse is equal to O2 A2 O2 inverse. This is exactly what I have shown you now, right? So that means, because these are all invertible, so A1 is equal to O1 inverse O2 times A2 times O2 inverse O1, right? And now if you call this, let us say this is T, right? So if this is T, then O1 inverse O2 is equal to T inverse. Check. How do you check? You just pre-multiply this or post-multiply this with this. So you take O1 inverse O2 times O2 inverse O1, it is a no-brainer that this will give you identity, and finally this and this will also combine to give you identity, yeah. So this is the identity. So therefore, I have found you, at least in the A matrices, so later on in the next lecture we shall see more of this, but at least in the A matrices I have found you that they agree, right. So therefore there exists a similarity transformation insofar as the A matrix goes, but we are not done yet, because we have still to verify that there do exist the B and C matrices also, which can be transformed from one to the other using the same similarity transformation. So the picture is not complete yet. We will see more of that in the next lecture. Thank you.